So we also use them in induction cooker. And the next type of region, the next zone, that is the visible light. The fourth zone is the visible light. The example is light. The fifth zone, under fifth zone, it's the ultraviolet region. Ultraviolet region, or the ultraviolet waves. And then we have the X-ray region, X-rays, and the gamma rays. So these ultraviolet, X-rays, and gamma rays, they also have a number of applications. Okay. So we didn't list them, but there are a lot, because some of them we will be studying later also. Okay. Let's write a note. Note number 1. Wavelength of visible light ranges from 380 nanometers to 760 nanometers. Next point, X-rays and gamma rays Hannah, I didn't get your question. You're asking whether to note this down. For ultraviolet, X-rays, and gamma rays. So it's including all. You're asking these regions, radio wave, microwave, infrared, all of them are regions. Okay. So here we have this spectrum, right? In this spectrum, if we start from this wavelength to this wavelength, in between, so this is 10 to the power 3 meters. That means 1000 meters. And here it's a 1 meter. 1 meter. So in between these two wavelengths, we can get several waves, right? We can have several number of waves. You can have a wave that has a kilometer of wavelength. Then you can have a wave that has 50 meters of wavelength or 25 meters of wavelength. Yes, Hannah. So note them down. Whatever I am writing, note it down. If you all no need to note it down, I will just mention and take the screen to a side and write over there. Okay. So Hannah, have you noted, or do you need to note them? And Atif, uh, our eye, our eye can only sense a certain wavelength. Okay, up to a certain wavelength only it can sense. So whatever above that wavelength is not visible, and whatever that is less than that wavelength is also not visible. Just like our hearing, we can hear between 20 hertz and uh, 20 kilohertz, right? So whatever that is below this, we cannot hear. Whatever above this also, we cannot hear. So there's a range where our ear is sensitive. Just like that, we have a frequency or wavelength up to which it is sensitive. So whatever below that or whatever above that, we cannot sense them. Okay, Adif, have I cleared your doubt? Why other lights are not visible? Hannah, how about you? Have you noted or you have to note? Uh, Below infrared, this one's. Okay, quickly note it down. How about the others? So within this range, only it is visible. And next, extra X-rays and gamma rays. And gamma rays. They have high penetrating power. Have high penetrating power. They can move through. They can move through very thick materials like concrete and all. These X-rays and gamma rays can propagate through. But other lights, they are not able to propagate. For example, just think about visible light. Will visible light go into concrete? No, right? It cannot go into concrete. But X-rays, X-ray can go up to a certain level, but gamma rays, then they can go much deeper. Okay, that is what is meant by uh, penetrating power. Third, so you'll have a question. Use the common knowledge or the general knowledge and tell me if electric field and magnetic field will affect electromagnetic waves. Will they affect? External electric and magnetic field do or do not affect EM waves. Okay, now let's think. They won't affect, right? So what's the easiest example you can take? Think about light. Think about light. Can you, using a magnet, can you affect the light, the direction of light? No, right? So it do not affect EM waves. So next subtopic, light. Now we are going to talk about visible light. Subtopic, light. EM waves in the visible region, EM waves in the visible region is referred to as light. Is referred to as light. So next question, can we see light? Can we see light? What is your idea? Real thing, can we observe light? So the answer is interesting. We cannot see light. Okay, the answer is we cannot see light. So let's write down, light is a form of energy, is a form of energy that gives us which when entered into our into our eyes gives us into our eyes gives us the sensation gives us the sensation of sight. So it's still hard to get it right that we cannot see light. When I say light is not visible, it's sort of you're not able to digest it. So have you ever played with laser lights? This laser light or this laser toy? So this laser toy, now think a little, recall the memory and tell me, when you shine this laser light, do you observe the path of the laser light or only a spot on the wall? Which one do you observe? Do you observe both of them or only a spot? What do you observe? So obviously you are going to observe the spot only. If light was visible, if light was visible, you should have uh, observed this one also, right? You should have observed this path of light also. But instead, you only observe this spot. So the idea is simple. When light reflects off a surface, when light is reflecting off a surface, so you're over here, your eye is over here. Let's say your eye is below here. And when this light reflects off the surface, it gives the sensation of this point only where it reflects. It is giving you an idea about the surface. Not actually, you're not actually looking at the light. You're actually looking at the surface. Okay, so we cannot see light, but light gives us the sensation of sight. So Imla said that uh, we cannot observe light, but because of light, we are able to observe. Okay, so that's the idea. We cannot observe light. We cannot observe light. But when reflected off a surface, but when reflected off a surface, the surface can be seen. The surface can be seen. Yeah. So Atif says, in some, the path of the light is also visible. So, Atif, you might have seen some videos, right? So in those videos, just to show how this light travels, what they do is they shine this light inside a room where they is filled with smoke. So when this light hits this smoke, it will reflect back. So what you actually observe is the smoke, not the path. Okay. So just now, whatever you thought about light is going to change. It is going to entirely change when we study this section. When we are finishing off this section, we will understand that whatever we look is not real, but it is an illusion finally. So we cannot observe light, but when it is reflected off a surface, the surface can be seen. Next point, quantum of energy, quantum of electromagnetic energy, electromagnetic wave energy is a photon, is a photon. You might have got an idea about quantization, right? In chemistry, I hope. So quantization means we take certain physical quantity and get its fundamental unit, a fundamental amount. You cannot further divide it. So that is the smallest unit. For an electromagnetic wave, the smallest unit is a single photon. So electromagnetic wave is composed of several photons. And we know the equation for the energy of a photon. That is E is equal to HF. where h is the Planck's constant. Planck's constant. So the value of Planck's constant is 6.63 into 10 to the negative 34 joule second. Where E is the energy of a photon. That is very important. Of a single photon. But we know that C is equal to F lambda. But C is equal F lambda. Speed of light is equal frequency into lambda. So we can replace, therefore, E is equal, instead of F, I can write hc over lambda. Instead of frequency, we can substitute C over lambda. So replace E is equal hc over lambda. Then for the energy of a photon, we have two equations. E is equal hf, E is equal hc over lambda. Quantum means, now we are talking about energy, right? The energy of a wave. So let's say we have 100 joules of energy. This wave, the wave has got 100 joules of energy. So this 100 joule of energy is not continuous. They are just like small bundles of 10 joules. We have small bundles of 10 joules. We have such 8 more packets. Okay. So I have 10, 10, 10 joules, 10 packets. So here I have drawn 2. Therefore, there are 8 more remaining. And I cannot further divide. I cannot take 5 joules. I won't have 5 joules. The smallest unit is 10 joules. So if this wave is going to get some more energy, the possible values are 110 and 120. How about 115? Is it possible? Is 115 possible according to my example? No, because the smallest block you can have is 10 joule. The smallest you can have is 10 joule. So 115 is not possible because you cannot further divide it. So just like that, this smallest unit are dividing into small units. If some physical quantity can be written as Q is equal N times E. That means this is the fundamental. This is the smallest value. And this is an integer. And this is the quantity. Okay. If I can write in this manner, then we call the physical quantity is quantized. Okay, the physical quantity is quantized. That means it is a multiple of the smallest unit. So you won't have halves or 3/4. You're not going to have fraction at all. You will always have integers, integer multiple. Then this smallest unit, we call this smallest unit as the quantum. You cannot further divide it. Okay. So for this electromagnetic wave, the quantum is a photon. So you cannot divide a photon further. If we have a photon that has, we have a photon that is having 5 joules of energy. So that wave can have 10 joule energy, can have 15 joule energy, and so on, but it cannot have 14, 13, 12, 11, it cannot have those energies. Did you get the idea of a quantum, Atif? How about the others? Hana and Najima? Welcome. Uh, no, Najma, I was telling like this. Now let's say it is not always 5, okay? It depends. Now in this example, the quantum is 10 joule. In this example, the quantum is 10 joule. So the possible values for energy of a wave is 20, 30, 40, and so on. For this example, the quantum is 5. Therefore, the possible values will be 5, 10, 15, and so on. If the quantum is 2 joule, then the possibles will be 2, 4, 6, 8, 10, so on. So this smallest value, that one we call as the quantum. Got it, Najima? So it is just an example. When I choose numerical example, it is easy to understand. Okay. How about Hana? So let's write a knot. Knot number 1. Let's say we have red light and blue light. So red light will be composed of photons, small photons. And those photons and blue light will be composed of another different photon. So if you take a red color photon, let's say it has energy E1, then the next red color photon also has the same energy E1. Because this one has frequency F1. The blue color light, it has frequency F2. So it will have energy E2. The single photon will have energy E2. Whose energy will be greater? We know that the frequency of blue light, frequency of blue color light is greater than the frequency of red color light. Therefore, energy of blue color light will be greater than the energy of red color photon energy. So below we can write each and every photon of a monochromatic light will have the same energy. But different colors will have different photon energy. Are you clear with this note? Just go through and let me know quickly if everyone got the idea of the note clearly. Yeah, when we say monochromatic means it is a single color. Monochromatic means it is a single color. So here red color is monochromatic. Only one color. Chromatic means color. Mono means single, so single color. Did you get this first point? Each and every photon of a monochromatic color, monochromatic light will have the same energy. That means if you take red color, now this red color light will have many photons. It will have many photons. Each and every photon will have the same energy. Why is that? Because E is equal HF. That is the energy of a photon. Energy of a photon, E is equal HF. For red color light, we will have a constant frequency. We will have a certain frequency. This is constant, therefore this is constant. So this photon, each and every single photon will have certain energy E1. But when we take a blue color, for blue color, frequency is high, therefore energy is high. Then this red color photon and blue color photon, will they have same energy? Will red photon and blue photon have same energy? No. Is everyone clear with that idea? Hannah and Atif, how about you all? Is that idea clear? That red color photon and blue color photon, you're asking what is monochromatic? Monochromatic means, Atif, you're okay with monochromatic or not yet? Monochromatic means single color. Now, sunlight is not monochromatic because sunlight you can disperse into several colors. So it is not monochromatic. And your screen is not monochromatic because it has multiple colors. But the old screen, black and white, that is monochromatic because only white is actually working. The other one remains black. Okay, so that is monochromatic. How about Hannah? Whatever studied today, is it clear or you all have any doubts in that section? We have a second note. That's a small one. I will note it down and ask you. Okay. Now let's say we have a source, electromagnetic source. So this electromagnetic source is giving away photons. So this is an electromagnetic source. let the rate of emission of photons be n, then power is equal n times E. This is energy of a photon. Energy of a photon, that will be in joules. This is the number of photon per second. Therefore, this is per second. Then power is joule per second. If the energy of a single photon is E, and in 1 second this electromagnetic source produces 100 photons, the power of the source will be 100 times E. Okay, that's the simple idea. We are clear with whatever we discussed today. Do you all have any doubts? And how about the session? Is it clear and writing on the screen? Do you all find it hard or it's convenient? Can you all let me know your feedbacks? Okay. And how about the time I give you all to note down? Is it fast, slow? Yeah, I'll be discussing the questions also from the paper book. So try the questions. There might be some questions related to this section, statement-wise questions. So go through them. We can discuss them. How about the time? I mean, the time I give you all to write it down. It's enough, right? When you get used to, I'll just speed up a little. Other than that, no issues, right? Okay, so in a minute, the meeting will end. Not 2 hours permanently. For now, I have a 23 batch. There are 2 or 3 sets in 23 batch. So once their syllabus is over, I will increase the number of hours. Okay, Hannah. So that's all for today.